Hello everyone. Today, following up on subroutines, I want to talk about a topic that might be new to everyone, and that is the topic of interrupts. Okay, so to start, I want to talk about interrupts in the context of our day-to-day lives and compare that to what goes on in our processor with respect to interrupts. So typically, our phones, if you're sitting in a classroom lecture or in a movie theater or wherever the case may be, and you're expecting a call or a phone call or a text, you might put your phone on silent, completely on silent, no vibration, anything. And in that mode, the only way that you would know that a call was coming in or a text was arriving by continually checking your phone by looking at it to see if a call or text arrived. Okay, that is similar to what a processor might need to do if it wanted to check the status of an input to see if an event has occurred, a button has been pushed, some other data has arrived on the serial port. That's called polling. Okay, and it is to check repeatedly, poll to see if an event has occurred. Okay, and as you can imagine, this is going to be time consuming. If we are continually looking at our phone, our cell phone if it's a movie theater, it's going to be annoying to the people around us, but it's also going to distract us from our other tasks, maybe watching the movie in this particular case. So it's time consuming, and depending on how quickly you check or poll for the occurrence of an event, a call or a text, you could in fact miss that event or be delayed in responding to that event. Now, the alternative is that you maybe in the movie theater, maybe just put your phone on vibrate. So when that call or text comes in, now you don't need to continually look at your phone. You will be made aware of that incoming event through that vibratory signal, and you will be interrupted with your current task, watching the movie maybe in this case, and be able to respond to that incoming event. Okay, so this is similar to how a processor would handle the occurrence of an event through an interrupt. Okay, so this is a signal that is automatically generated. Okay, like the vibration on your phone, it would be automatically generated once it's enabled. When an event occurred. Okay, so there are many advantages to this approach. Again, we can keep ourselves busy with other tasks, just like the processor can keep busy with other tasks, and we can just automatically be made aware that an event has occurred through this interrupt. Okay, so let's talk about the things that make interrupts possible. Okay, so we'll kind of start at the end maybe and talk about what we would do once this interrupt event has occurred, or this interrupt signal has occurred, how we would handle the event. So in the case of your cell phone, when you the text maybe arrives, you get that vibration, you are, maybe automatically going to pull out your phone and respond, but you're going to service that event. Okay? In the processor, we handle the event through an interrupt service routine. Okay? Notice the word routine. It is a subroutine. We often abbreviate interrupt service routine ISR, and it's a subroutine that is called automatically. So I don't have to make a call to it in the code, so it's not going to be called periodically each time we hit the call to whatever the subroutine might be labeled. In this case, it's going to be an automatic occurrence that occurs when this interrupt signal arrives. Okay, and the generation of this interrupt signal, this is done in hardware, right? It's not a software handled signal. We have to enable it in software, but it's hardware that generates that interrupt. So there's no software overhead, no software that needs to be written to make sure that signal gets generated. Now again, we do need to enable these signals to occur, and let's talk a little bit about how that might be done. Okay, so there are kind of two main categories of interrupts. Those are maskable interrupts okay, and these are interrupts that can be disabled. Okay, or ignored. So maybe your incoming text, maybe you want to, although your phone will get notified, even in fact if it is on silent, your phone would get notified and a message would come up, but you could ignore that. You could ignore it even by just shutting the phone, putting the phone completely on silent. So you have the option to disable or ignore that interrupt, and that's what the equivalent of a maskable interrupt in the processor. It's one that we can disable or ignore. Now, on the other hand, if you're in the movie theater watching the movie and maybe the smoke alarm goes off, that is an interrupt or an event that we probably shouldn't ignore, and is the kind of the equivalent of a non-maskable interrupt in a processor. And this is description of a non-maskable interrupt is interrupts that cannot be disabled. Okay, so pretty straightforward, and we'll look at how interrupts can be enabled and disabled here, at least in the NIOS 2 specifically here in a second. Another aspect of interrupts that can be should be considered is interrupt priority. Okay, so maybe on your phone, you have a couple of different events that you are waiting to have come in, or that you're waiting for. Maybe a text and a phone call, and maybe from different people. And so when the signal occurs, whether it's the ring of the phone or the vibrate of the phone, with the occurrence of one of those events, maybe they both happen simultaneously. Maybe your text comes in and the phone starts ringing for a phone call at the same time. Well, the phone call really can't wait for a response. The caller is going to hang up, and if it's important to you, you would probably prioritize the phone call over the text, because the text could be delayed briefly, and there's no harm done. Even higher interrupt priority again might be the fire alarm, right? The fire alarm occurs, we may ignore all other interrupting events and respond to the fire alarm, probably through leaving the premises. Okay, so interrupts can be prioritized, or in other words, ranked in order of importance. Okay, such that more important interrupts are serviced first. Okay, and we can look at some examples of how that might happen here in a second. Now, one thing we should note, again, notice I talked about my interrupt service routine, that code that's automatically going to be called, right? That subroutine that's automatically going to be called. We don't know precisely when that might occur. It's not going to necessarily occur right after line 10 of our code. It's an asynchronous, potentially an asynchronous event that's going to occur. If it's associated with the press of a button, that press of the button could occur at any point through the flow of your code. So because of that, it's an absolute necessity that no registers are affected by an interrupt service routine. Why? Because we don't know when it will occur, so we don't have the ability to plan to make sure that those registers aren't being used when it occurs. So it's very important to push and pop any registers that are going to be affected by our interrupt service routine within the ISR. Okay, and as I said, it's because the ISR can be called at any time and from any place in a program. So with although we now know how to use push and pop, and hopefully we make use of those even for normal subroutines, we could be strategic and say, oh, okay, well, this subroutine, I'm going to always call it right here in the code, so I'm just going to make sure I'm not using the registers that are affected by that subroutine. Okay, we don't have that luxury with an interrupt service routine, so we have to make sure that none of our registers are affected, so we need to use push and pop, or the equivalent of a push and pop function. Okay. Another aspect of interrupts is interrupt number. Okay, so typically, and I'm going to show you a block diagram of what the NIAS2's interrupt hardware looks like, and we'll see that typically there's only one interrupt signal line that's typically on the control bus. So one interrupt signal line on the control bus that's shared by all devices. Okay, and to determine which device caused the interrupt, each device has an interrupt number associated with it. Okay, and we'll look at how that's done through evaluating various registers. Okay. Okay. Again, we'll look at some examples of the NIAS2, and well, maybe I'll do a tutorial looking at interrupts in a PIC microcontroller as well. But we'll look at these after I've introduced a few more of the components here. Okay, so in the NIAS2, there's often going to be some form of these type of registers in any device, but we're going to look at the names of them specifically for the NIAS2, and these are the interrupt enable. Maybe I should call these enable registers. Okay, so down at the device level itself, so it might be an input, it might be a classic input port with buttons attached. It may be a device like a timer, which you're looking at in lab 3. It may be a serial port that will have the ability to have a interrupt set at the device level. Okay, so those are what we would refer to as a device interrupt mask. Okay, and the specifics of what bits within the register, what they're associated with, will be different for every device. And again, we'll look at a couple examples here. Okay, so this is a register within a device. So this would be an example of a configuration register, maybe say a config register. the register may in fact be a combination of a config and a status register, but for our purposes we're talking about configuring the to enable interrupts from a device. So this would the particular bits that we are talking about would be associated with configuring it. So config register within the device, which determines which pins, I'm going to say, or actions, if any, right? We don't necessarily have to have any pins or actions enabled to generate an interrupt at the device level. So any pins or actions of an input port which ones can cause an interrupt. Okay, so that's down at the device level. Again, whatever that might be, input port, timer device, serial port, and the list kind of goes on and on. Okay, the next is at the processor level. Okay, and here's where we can enable or disable which interrupt numbers are capable of or allowed to generate an interrupt. In the NIOS 2, this register is called the IEnable register. Okay, and again, I guess this is specific to the NIOS 2. It's a 32-bit register. In the processor, again, keep in mind the 32-bit register is specific to the NIOS 2. It's going to vary in size and in configuration procedure for the various processors. So in the processor, which determines which interrupt numbers will be acknowledged or ignored. Okay, so which are enabled. Okay, maybe interrupt 1 is enabled to permit it to generate an interrupt. Maybe interrupt 0, 2, 3, 4 are all disabled and are not allowed to generate an interrupt. Finally, there is kind of generally one overriding register, often a single bit, that allows the generation of interrupts entirely or not. Okay, and this is in the NIOS 2 called the processor interrupt enable bit, and said it does just that. It enables the occurrence of all or no interrupts. Okay, so this is a bit in the processor. In the case of the NIOS 2, again, we should just say this is specific to the NIOS 2, but there will be some form of this in any processor. In the case of the NIOS 2, it's a bit in the processor status register, which determines, maybe should say controls, if all interrupts are acknowledged or ignored. And that's really all that are enabled downstream from this bit, right? With which all that are, they will only be acknowledged if that interrupt number was enabled, and then for the device associated with that interrupt number, if there is interrupts enabled at the device level. Okay, let's have a look at an example of what the hardware looks like at in the NIOS 2. Okay, let me take a screenshot of this so I can mark on it. Okay, so we see kind of all the different aspects that we're talking about here. Here's that processor interrupt enable bit. Okay, here, well, I guess first of all, here's this common single interrupt line that is shared by all devices and all interrupt numbers. And if I can disable the occurrence of any interrupt by simply putting a low on that processor interrupt enable bit, and having a low on this input will mean that nothing will be able to get through to activate the output of this AND gate. Now this is a block diagram, and the actual hardware, the upstream here is probably not specifically a multi-input OR gate. In fact, this is probably implemented through a wired OR configuration, implemented with wired OR outputs. From open collector gates. Okay, so each of these I pending bits that's coming in from each interrupt number is probably said coming from the output of an open collector gate, you know, associated with interrupt 0, 1, 2, and so on. And these open collector, this is often how it's done. I actually don't know for sure that that's how it's done in the NIOS 2, but it is probably pulled up. Each of those outputs is pulled up through an external pull-up resistor, such that if any one of these open collector outputs goes low, it will cause the entire bus to go low and generate a interrupt. And again, the interrupt is probably an active low output, contrary to what's shown in this diagram. Okay, so just like to bring that up because that's a really common example of open collector, the use of open collector outputs to have multiple outputs tied together to generate one common signal. Okay, so we see the processor interrupt enable mask, which is called IEnable. We see that register up here. So there's 32 bits in this register, and it's those bits when they are 1. If we have a 1 on the least significant bit, that's going to put a 1 here and allow, now this should really be shown as a bus. There should be, should be all separate connections to each of their associated hardware devices, right? So this is actually multiple 32 line bus, so that's a little bit misleading. But when we enable bit 0 in the I enable register, that allows the interrupt from interrupt number 0 to be passed through and set a bit in this I pending register. And we haven't really talked about the I pending register yet, but that is the register that keeps track of which interrupt generated, which device, or which interrupt number, I should say, generated the interrupt that ultimately occurs on this common shared line. Okay, the other thing we don't see here is the device level interrupt mask. Okay, so somewhere back here there's devices that are enabled that are able to enable or disable the occurrence of interrupts for different aspects of the hardware, or different inputs of the hardware potentially. So if we go to lab 4, for example, we're going to be dealing with interrupts on one of the input ports that's used for buttons, and here is what the here's what the hardware might look like within that device at the device level. Okay, so here we see the device interrupt mask, because this device has the ability to enable whether bit 0, for example, is able to cause an interrupt and send that interrupt through to interrupt number 1 that we saw on our other diagram, right? So this signal here corresponds to a signal coming in on this line 1 of this external hardware interrupt request line, which ultimately makes its way to here. Okay, so this diagram here is showing just one of the many bits that's there to enable the occurrence of that interrupt associated with line 0. But if we look up here at the actual registers associated with this hardware, this input port, we'll see that there's an interrupt enable bit for each of the 4 bits of the 4 push buttons that we have in the hardware. Okay, so this hardware would be duplicated 4 times. The other thing that we see here is that so we saw back, maybe go back to this diagram again, we saw back here that there's a I pending register that keeps track of what interrupt number generated the interrupt. But once we get to the device, we still need to know which specific bit within the device, or in this case, which specific push button within the device generated the interrupt from interrupt 1 in this case, right? So the device itself has a a interrupt pending register that stores that particular bit caused the occurrence of an interrupt, and we see that that's a separate register within the device, that when that bit is 1, that tells you that that bit or that switch in this case generated an interrupt and it's waiting to be serviced. Okay, you might ask, how did I know that this was connected to interrupt 1? Well, if we go to what do I want here? If we go to the CPU simulator, we see that over on the push buttons, maybe I can zoom in on this? Maybe I can't. On the push button hardware here, oh, it's actually frozen, that it lists which interrupt this particular device is associated with. We see the push button switches, for example. Oh, let's try again here. Sorry. We see down here, now I can zoom in. We see that the push button switches, right beside their address here shown on the right, it shows which interrupt number it's associated with. Same with the JTAG interface, is associated with interrupt 8. The interval timer is which is being used in lab 3, although we aren't using the interrupts. It's associated with interrupt number 0. Okay, so that's something that will always be provided in the documentation for your processor, what interrupt number each of the devices in your system is associated with. Okay, one other thing we need to consider when handling interrupts or dealing with interrupts is the way in which our processor deals with interrupts and in terms of the location of the interrupt service routine. So there are two kind of main ways of handling interrupts in software. So let's describe those a bit now. And I'm actually, the first one I'm going to describe is going to be the means of handling interrupts that is not done in the NIOS 2. And that's through the use of an interrupt vector table. Okay, so with an interrupt vector table, the nth interrupt service routine is located at the nth, whatever number interrupt is generated, at the nth entry in a long table. Okay, and the and maybe I should say, rather than the nth, ISR is located at the nth entry in a long table. It's really the this is really the address. Let's leave it like this for now. And we'll come back to revisit this in a long table. So this table is referred to as our interrupt vector table. Okay, and this table exists in memory. Okay, interrupt vector table will often abbreviate this as just IVT, interrupt vector table. Okay, so what happens is that when the nth interrupt, again, whatever number interrupt we determine or the system determines to have occurred, the nth ISR is called directly by jumping to the appropriate entry to the address of the nth entry in the interrupt vector table. Now, what in fact generally happens is that entry in the interrupt vector table does not contain the entire interrupt service routine. It'll have a branch instruction or a jump instruction that will, from that entry, branch to the location of the actual interrupt service routine. Okay, so what gets stored in that entry in the table is actually the a branch to the appropriate location where your interrupt service routine, where the code that's associated with how you want to handle that occurrence of that particular interrupt, where that code actually exists. Now, this is one very common way to handle interrupts in processors, but in fact the NIOS 2 does not do it this way. It does not have an interrupt vector table. In fact, all interrupts jump to the same address, and that address is 20 in hex. When we get to that location in memory and execute the code that resides there, we have to decode which event actually caused the interrupt to occur, or which device actually caused the interrupt to occur. So we will have to, through reading of the I-pending register of the processor, determine which interrupt number caused the interrupt, and then based on knowing we can then map that to a particular device. We showed that if we go back here again, we showed that in the case that we decide that it was interrupt 1, we would know, okay, interrupt 1 in our case is associated with the push buttons, but if we have interrupts enabled for all 4 push buttons, we would have to read the I-pending register for sorry, I wanted to bring that up, the I-pending register for within that input port to determine which of the actual switches caused that interrupt to occur. Oops, I'm just looking for a block diagram associated with our push button interrupt. Okay, so once we determine that it was IRQ1, say okay, that's the push buttons, but then we would need to read the I pending bits to determine which one of those 4 push buttons, if they're all active, caused the interrupt to occur. Okay, so whereas an interrupt vector table, we would know immediately which interrupt number triggered the interrupt. That would be decoded in hardware and would jump us directly into the appropriate interrupt service routine, where there we may have to do some further decoding of which, in the case of the push buttons, which push button caused the interrupt, but we would immediately get into an interrupt service routine that was specific to at least that interrupt number. Okay, so decoding of the appropriate action performed in software, and like we said, this would be done through checking the I pending register, and that may be the I pending register of the processor and the I pending register of the input port itself. Okay, let's look at what happens when an interrupt occurs in the NIOS 2. I'm just going to pull this directly out of the course notes because it's precisely what we want to discuss, and there's no point of writing it out. So this comes from section 9.3.4. You can write it out again if it helps with you remembering the steps, but I'm going to just copy and paste it in here. So when an interrupt is generated and acknowledged in the NIOS 2 processor, there's a sequence of events that occurs, and it's important to appreciate precisely what happens when those events occur. The first one, and I want you to take notice of this statement because it has implications that we have to account for, is that the current instruction is stopped immediately. And here's one of the key things we need to remember. That instruction's left unfinished. Okay, so whatever instruction we were currently executing in the code, that didn't complete. So we need to be aware that we have to come back and redo that instruction because it wasn't done. Okay, from there, and this is all happening in the at a hardware level. We aren't writing code to do this, but these are the things that happen. The instruction pointer is saved to the exception return address. So different than the return address, there's a separate register that holds the return address for an interrupt, and that is the exception return address register, EA or register 29 if you are looking at the registers. Okay, now, and this again is an important point. Since the instruction pointer already points to the next instruction, we have to make sure that when we do a return from our automatic subroutine, this interrupt service routine, that we adjust this return address by subtracting 4 from it, so we go back and complete that instruction that was interrupted. Okay. Next thing, the processor saves the status register of the NIOS 2. Now, if we look at the status register of the NIOS 2, so in the introduction to NIOS 2 processor document that you can find on D2L under reference documents, you'll see that the status register here is listed as a control register, although it's not really so much a control register as it is a status register, and hence the name, we note that, let me make it so I can write on this document here. We note that the status register here only has 2 bits that are meaningful at all. The other 30 bits just say reserved, so we don't care about this. This bit tells the whether the processor is in user or user mode or supervisory mode. We really don't care about this bit. So the only bit that's of any relevance in the status register is actually the processor interrupt enable bit. Okay, so when the status register is saved, it's saving the status of whether the processor interrupt enable bit is enabled. Just of note here, you'll see these other control registers in here, and a couple that we've have just been talking about is that interrupt enable bits and those I pending bits. Okay, so if we go back here, so we said that the processor saves, and again this is all done automatically, the processor status register into the E status register. Okay, so we have a backup of the status register, and then it alters the status register by setting the processor enable bit to 0. So this disables the occurrence of further interrupts while we're in the interrupt service routine. Okay, so this will disable interrupts. Okay, note that the copy of the stored status register has the processor interrupt enable set to 1. Otherwise we would have never got into this interrupt in the first place. And finally, again, automatically the processor branches to address 20 hex, where our interrupt service routine will be located. Okay, so again, that's all automatic, completely done in hardware. The current instruction being executed is interrupted and left unfinished. The instruction pointer or program counter, whatever you want to call it, is saved in the exception return address register. The status register is saved in the E status register, and the processor interrupt enable bit is set to 0 to disable further interrupts. And then we branch the address to 0. Now that's fine. We get in there, we handle our interrupt with whatever code that we write at address 20. But the final instruction, well, maybe the final 2 instructions that we want, the very final instruction is going to be an E return instruction. This is going to take and return the program counter to the value that's in the EA register, and the and restores the processor status register. So processor status register is restored. So the PIE, the processor interrupt enable bit, gets set back to 1, and the exception return address register gets put back in the program counter register. Now, again, recalling that the we need to make sure that we subtract 4 from the exception return address register before we put it back into the instruction pointer or program counter, to ensure that the address, or sorry, the instruction that was interrupted, that was left unfinished, as we said up here, gets that we load back up the address of that instruction, refetch that instruction and redo that instruction. Okay, so if I pull an that's from the course notes, let me just paste this in, we can see what an interrupt service routine might look like. Okay, so one of the first things you note is that the interrupt service routine is located where it needs to be for the NIAS2 processor. We've used the .org directive to locate the code at the address 20 in hex. So that's where the interrupt is the generation of an interrupt is going to force the processor to jump to this location in memory. So this is where our interrupt service routine should reside. Now, in this particular interrupt service routine, we're using register 3. So we made sure to push R3 at register 3 at the beginning and pop it at the end so that it's not affected. Within the interrupt service routine, you see we're decoding to find out where the interrupt service routine came from, or where the event came from, what interrupt number. Right, so we use a read control register command to read this pending register, store it in register 3. In our case, maybe we are only interested in handling an interrupt for interrupts on interrupt number 2. So we mask the value that we read in from the pending bit to set all bits but the third bit, the bit associated with interrupt 2, to 0. And we say, well, in this case, we have a branch if equal to 0. So that would mean that if the third bit in register 3 was not 1, we will end up having register 3 equal to 0. In that case, we'll say, well, it was not interrupt 2, so we're going to branch to this location and just bypass the handling of interrupts from interrupt 2. If it was from interrupt 2, we may do something that as required for interrupts that come from interrupt 2, and execute some additional instructions. In this case, we actually don't show what we might do to handle that interrupt. Again, it could vary widely depending on what the intention is on when interrupt 2 occurs. Maybe interrupt 2 is associated with a button or a serial port, who knows. But we also note that we're going to, at the device level, we're going to read in the address of that particular device. In this case, we're calling it my port. And here, it so happens in the hardware in the lab that the pending bits for this particular port exist at the base address of the port plus 12, and we are clearing the bits to basically show that we have dealt with that interrupt and that we're going to move on. One thing you might have noticed is we only cleared the interrupt pending bits within the device itself. If we go and look back at our hardware here for a second, we see that the I-pending bit at the processor level gets set from each of those lines that comes from the different devices associated with each interrupt number. And if we go and look at how that is generated, here's the hardware that is generating the enabling a bit or setting a bit in that I-pending register within the processor. So if we clear all of the pending interrupt bits down at the device level, all of these bits that are triggering the interrupt line that's associated with the processor level interrupt bit that flags that I-pending register will get disabled, and that I-pending register at the processor level will be cleared as well. Okay, so we don't have to explicitly go and clear the I-pending bits at the processor level. We just need to clear all those I-pending bits, however many there might be, at the device level. Okay, so that's I guess important to recognize that there's kind of two levels of I-pending registers. That some are at the main one at the processor level, the first one where you need to decode to figure out which interrupt number generate the interrupt, and that second level that's at the device level. And if we go back here, and look at if we look at the lab manual, this is lab 4, we see these pending interrupt bits for the push button port reside at an address that's again offset by 12 from the base address of that port, right? And we can look at that port here in the hardware, and we see that the port's address is 1000050, right, as is stated here in the lab manual. And the interrupt enable bits are offset by 4 from that address, so we can pick and choose which of the bits or which of the switches we want to be able to generate an interrupt, and then we can read the register. Really, it's a status register. We can read the bits to determine which one of those bits or which one of those switches generated the interrupt when an interrupt from, in this case, interrupt 1 is generated, right? We see that it's interrupt 1 that is triggered by the push buttons. Okay, you will also discover in this lab that we'll be using the timer, and we'll be using the interrupts from the timer. Use the timer also in lab 3, but we actually disabled the interrupts. So there is some example code on what the interrupt service routine might look like for the interval timer. And again, here you see the interrupt service routine, as all interrupt service routines are for the NIOS2, are at address 20 in hex. We pushed the return address register and register R3 and R4. This return address we push to make sure if we want to call a subroutine from within the interrupt service routine, that we don't corrupt any value that is already in that return address register, because this interrupt service routine could occur while in the middle of another subroutine. And you see here's a subroutine call action 0 here within this interrupt service routine. And again, you'll see that we determine the source of the interrupt. So here we check the pending register, and then we specifically check to see if it's coming from interrupt 0. Again, if we go back and look here, we'll see that the timer is associated with interrupt 0. And in the lab, you'll see the registers that are associated with the timer, and it's in configuring that timer. But we can have other interrupt handling of other interrupt numbers within the same interrupt service routine as well. For example, we're going to want to add handling of the interrupts for the push buttons, and that can be put in this same location. We just need to check the pending register again, mask the bits to see if it came from the push buttons, and then perform an appropriate action if it's for the push buttons instead of for the timer. One thing that we talked about was interrupt priority. If we have an interrupt vector table, often interrupt priority is programmable, sometimes in the device, or sometimes based on the interrupt number. Often lowest numbered interrupt has the highest priority. In the NIOS 2, simply through the order of which we check the pending bits, we can set our interrupt priority. So if we first checked interrupt the pending register for interrupt 0, well, we've just, through checking that bit first, we've just prioritized that interrupt as the highest priority. But we could have just as easily checked for interrupt 1 first and made that higher priority. While we're looking at the code, so here's our interrupt service routine. We can also look at what the setting up the interrupt might look like, or initializing the interrupt. This is our main program, but if we go back here, we'll see some of the details on setting up the interrupts. So we've put this in a subroutine in this case, but you see things like we are setting bits in the enable register here. We did that by first reading the enable register and then writing it with just the bit we want to change, so we don't alter. Maybe there's other interrupts enabled, we don't want to impact that. We can also see that in here we are reading another control register here, the status register, and then we go and set the least significant bit, which is a processor interrupt enable bit, to 1, and then write that back to the control register. So here we enabled interrupts. Oops, this highlighter isn't cooperating here, but we enabled IRQ0 by setting a 1 in the least significant bit of the enable register, and then we enabled interrupts in general for the processor in general, or all interrupts, by setting the processor interrupt enable bit. Now we don't show right here the configuration at the device level. In this case, we've just set up the interrupts for the timer, and that's done through this setup timer subroutine. And we go down and look at that, and there's some details about the timer that you can read yourself, but you can see that part of that is setting the interrupt timeout bit to 1, which is setting the timer to generate an interrupt when the timer times out. So you can dig into that further yourselves. Just kind of one final thing about interrupts. You're often going to see spec sheets give details on interrupt latency. So what does that mean? Well, interrupt latency is a measure of how long it takes a device to be serviced after it generates an interrupt. Okay, so how long it takes a device to be serviced after an interrupt is generated. Oops. Okay, so this can be important, an important spec. Maybe you need a certain response time for the system you're designing, and it can be important to know how quickly you will, and often how quickly you will get into the interrupt service routine, and often this interrupt latency is exactly that. It's not in fact how long it takes it to be completely serviced and the whole interrupt service routine to be run, because that can be variable and a function of the code that you write. So you have some control over that as a programmer. What is determined by the hardware is how long from the occurrence of an event until you enter the interrupt service routine, and you'll see that that is a spec that's often provided by processors. Okay, and if we can go have just a really quick look at the microchip processor as an example of interrupt latency, you'll see that it is something that there is some importance in. So you see here the interrupt controller, it says has 5 cycle latency. So that means that they are guaranteeing that you will enter the interrupt within 5 clock cycles, which is extremely fast. Okay, some other things you see here, spelling a typo here, but we can have 118 interrupt vectors. Okay, that suggests that it has an interrupt vector table, which it does. We can have 49 different sources of interrupts. Up to 3 of them can be external. And we have programmable priority levels, so we can program the priority levels of various interrupts through, there's actually a register to program them. And the processor itself can generate interrupts related to certain exceptions or unexpected events that occur in the processor that you may want to catch through an interrupt. Okay, so that's interrupts. I'll do a quick tutorial where we'll look at some of these aspects of interrupts for the microchip processor, just to contrast it against the NIOS 2, and we'll get into experiencing the NIOS 2 interrupts and handling of those interrupts in Lab 4.